Hi everybody. I'm going to introduce the beginning of one of the more important concepts we're going to do all year, the concept of momentum. And the reason we're going to do it now is we're going to take what we understand about the laws of motion and we're going to modify them a little bit. We're not change them, but we're going to look at them from a different angle. And the reason for this is we want to start looking at a phenomenon that is probably the most common in nature, and that's called collisions. All right, where two objects or two or more objects collide with one another, not to destroy each other, to break them into smaller pieces, but to change what they were doing. Okay, so a collision really is just essentially a force exerted on another object that usually happens over a short period of time. It doesn't have to be a short period of time, but generally that's what we associate with it. So collisions can be notoriously difficult to understand the outcome because it's really hard to measure the amount of force that one exerts on another. If, think of a bowling ball hitting a bowling pin, or an 8-ball hitting the 15 pool balls that are on a table. When you have that collision, you should be able to predict how every object is going to behave using the laws of motion. And our way of doing that is using the concept of momentum. So I want to start off with a fairly contrived situation, but hopefully it gets the point across of why we introduced the idea of momentum. So let's say you go to a fortune teller and they read your fortune, and one of the things they tell you is you will be hit by a moving vehicle somewhere in the parking lot of Big Lots over off of 5 and 20. Okay, so it's been foretold. Your fate is sealed. You have no choice. You can't do anything. It might happen tomorrow. It might happen 2 years, but you're going to get hit. But you have a choice of whether you're hit by a VW Bug, which is a small car, if you don't know, or a large UPS truck. And what would you choose? Okay, well, that's perfectly your opinion, okay? So some people might say, I'd rather be hit by the VW Bug because it's small. The other might say, I'd rather be hit by the UPS truck because a variety of reasons. And I want to simplify the situation. You're just going to be hit by the bumper of each vehicle. The bumper is the same height, etc. So what you should have answered is it depends. In other words, one might be preferable over the other. Again, you might say, I don't want to be hit by a truck because it's so massive. But then someone else might say, well, I don't want to be hit by another one because it's going fast. So since we didn't have a chance to discuss this in class, this kind of loses some of its power. But the point is, when you're talking about a collision and we're talking about impact force, so in this situation we want to minimize that, you'd think, okay, it depends on how much motion each vehicle has, right? If it's not moving, it's a non-issue to you. If it's not moving relative to you, then there's no talk of a collision. And so what motion depends on, most people think it depends on speed, and it does. How fast it's moving is definitely a measure of its motion, but there's something else that you have to take into account, and that's its mass. In other words, getting hit by a truck that's moving the same speed by a small car are going to give you very different results because the truck has more motion, in this case because it has more velocity for a given mass. So I'm using this to define the amount of motion as a new term, and as you probably already guessed, that's what momentum is. Okay, so if I were to ask you what was Mr. C to consider the definition of momentum, it's simply the amount of motion. Now, the better definition really translates into an equation. So I'm just going to give you an equation. There's really no way of deriving it. It's a first principle. So the symbol for momentum, let me put it right here, is a lowercase p. I'm not sure where that comes from, but it is. So the momentum of any object is very simple. It's simply the product of its mass and its velocity. Okay, as I mentioned before, the outcome of a collision depends on the momentum of the truck, which is a combination of how fast it's moving and its mass. And so when you calculate momentum, it's pretty simple. It's same units as mass, kilograms times velocity. So it's just called a kilogram meter per second. There's no special name. And also very important, it's been a while since we've talked about this because we've been focused on forces. It's a vector. And a vector means momentum has direction. You have to just consider its direction when you are talking about it. And we'll see where that comes up. So let's do some very simple problems. Okay, first one. Is it realistic for an ant to ever have more momentum than a bowling ball? Okay, think about that for a second. Pause. All right, I don't know how you answered, but the answer is yes. Okay, now the word realistic is important. It's not an issue of the ant moving fast enough to compensate for the bowling ball's huge mass. That would not be realistic. There's no way an ant's going to be moving fast enough for a bowling ball move down a lane. But It can be if the bowling ball, I'm just going to call it BB, has no velocity. In other words, if the bowling ball isn't moving, it has no momentum, even though it has a lot of inertia. So a lot of people will think automatically that something has momentum, but it has to be moving. So if the ant is moving, even with this tiny mass, it has some momentum. The bowling ball is not moving, it has zero momentum. Okay, we have a baseball. It's thrown, okay? And it has thrown with a certain speed, right? That's about 70 miles per hour. It has a mass, okay? What's its momentum? All right, that's pretty easy, right? If I just do P equals mv, that's going to be 0.80 kilograms times 30 meters per second, and that's 24 kilogram meters per second. So why do we care? All right, what is this telling us? I mean, the speed is important for the timing of when to try to hit the ball. The mass is not so much important, but if I'm hitting it, how it's going to respond is important. So why do we care about momentum? And is this a lot? And the answer in this case is no. It's actually a fairly small amount of momentum. And why? How do you know? Where does momentum matter? So in this situation, it's fairly easy to stop or even change. So what I'm trying to get at here is when we care about momentum very often is the ability to stop something fairly easily. And the more momentum you have, the harder it is. So what would be an object that would be hard to stop? Well, that would be like, let's say, a car moving. So a car with a mass of 1,000 kilograms moving even at 5 meters per second or 5,000 kilogram meters per second momentum is hard to stop than a small baseball. Okay? So again, it's not the greatest ways, but I'm trying to get you to understand the beginnings of why we care what the momentum of something is, as opposed to its speed. Next one, I got a 40-gram bullet. I want it to have the same momentum as a really heavy person walking slowly. So how fast must the bullet move? All right, so basically what I want is P of the bullet to be equal to the P of the person. And so how do I calculate each one? Well, that's just M B VB equals M person V person. Well, I'm just breaking it down, and I've got this information, and this information. I'm looking for V of the bullet. Only thing I got to be careful about is my bullet's mass is in grams, and this is in kilograms. So make the conversion, do the math, and if you do it correctly, okay, I want you to work this out for yourself. Okay, you should get about velocity of the bullet 625 meters per second. So it's got to be moving really, really fast to have the same momentum as a very slow moving person, simply because the ratio of their masses is so large. Another problem. Okay, again, these are very basic, but they're establishing a few things that we're going to be doing a lot more of. I've got a car moving north, okay, with a momentum now of 20,000 kilogram meters per second when it's hit head-on by a text messaging team. If it's, and this is the, I believe, the train, okay, or car, I should say, is immediately after is 500 kilogram meters per second south, what is the change in momentum? So change in momentum is simply a subtraction. So by definition, I'm looking for delta P. That's how I symbolize change. And we're going to see change in momentum is a very important concept in this chapter. That's by definition my final momentum minus my initial momentum. Okay, so simple enough. I have 20,000 beginning, 500 at the end. But I got to be careful of the direction. That's where the vector part comes in. So I'm going to say north is positive. Therefore, the momentum after the collision is negative. In other words, my change of momentum is negative 500 units minus 20,000 units. So that gives me an answer of negative 20,500 kilogram meters per second. In other words, that's a really large change in momentum. The simple mistake for kids to make is do 20,000 minus 500 to get 19,500. We have to be really careful of that. That's going to come up again and again. So that's your first warning. Okay, now that we have a basic understanding of momentum, let's look at situations where concepts of changes in momentum are critical. And I'm going to do problem 5 here and then stop in the tutorial, and then I'll pick up the next tutorial for the bottom part of the page. So let's say I have a 70 kilogram person, Biff, jumps from a tabletop to a forced platform. Remember the thing we used on the elevator. So he's jumping onto here by falling down. We want to know if he has a momentum of this based on the height that he jumped, therefore the speed that he achieved. And the platform stops him, and it takes him 0.3 of a second to make him go from moving to not moving. we can ask what force did the platform exert on Biff? So the common sense answer might be it's going to be simply the weight of Biff. I take that and multiply it by 9.8. But because he's moving, I think we understand that the force he's going to exert on a platform is going to be greater than the weight of Biff. Okay? Because he was moving. So how do we solve this problem? Well, we're going to do it the long way first. So we're going to do it a free force diagram. So upon hitting it, right, so there is going to be we want to know what force did. So what's acting on Biff? So Biff, we have the force of the platform, and then of course we have the weight on Biff. Those are only forces. So we can say the force of the platform minus his weight equals ma. Okay, and the platform force has to be greater than his weight because we're slowing him down. He's accelerating the opposite direction. So we're looking for how much force does the platform exert on Biff. So we're looking for this. So algebraically, that's simply equal to ma plus mg, Biff's weight. We know mass, we know a little g, we got to find acceleration. So separately, we're going to calculate acceleration of Biff due to the platform. Well, what do we know? Well, we know the time it took him to stop, so we're going to use a is delta v over t. So we know the time, that's right here. Well, how fast was he going? We're not given that. We are given his momentum. So we have to do a separate equation where his change in velocity, okay, is equal to his change in momentum divided by mass. In other words, what I'm doing is I'm relating momentum to velocity and change, right? So if p equals mv, then change in momentum can also be calculated as m delta v. All right, so now I got to do the numbers. So I got 350, so our change in momentum is 0 minus 350, because he went from 350 to 0, so his final is that, divided by his mass of 70. So that's going to equal negative 5 meters per second. That's his change in momentum. Okay, so I'm going to say the acceleration, therefore, is negative 5 divided by 0.3, right? So that's about 17 meters per second squared, and a negative. When I go to plug it into here, I'm not going to put the negative in there because I've already taken account the negative with this minus sign. In other words, I made the upward force positive, so I got to make the acceleration positive. That might be a little bit confusing, but don't get hung up on that. So the change from the force on the platform, is going to be Biff's mass, 70, times, and now I'm just going to factor out the m, and I'm going to put a, which is 17 plus 9.8, and then I'm going to multiply that all together. Okay, let me just look at my notes here so I don't have to do this all. And I get about 1,850 newtons, which is significant, right? It's much higher than Biff's weight. Because, and what I want you to understand about this, and this is really what I'm getting to all, is the reason it's so big is because this is so big because the platform changed Biff's momentum very quickly. And that we're going to see is a really important way of looking at a force. And then we can ask, what force did Biff exert on the platform? Well, that's the third law of motion. It would be 1,850 downward because of the third law. Okay, so don't forget about the third law. That plays an important role in many of these problems. Okay, so I'm going to stop here. That's your introduction to momentum and related issues, especially change in momentum, which we'll see plays a more prominent role in future problems.